All right, I think we are recording, and what we're going to do is just go over lab 7 just to get started with the closed population, and maybe we'll do a little bit with the open population, although that is actually easier than the closed population estimates. So I think in previous years, students have really struggled trying to figure out how to get the closed population estimate. That is the estimate of abundance that we're asked to do in part 1 of this lab. And it's the concept should be fairly straightforward, but implementing it in Excel requires a little bit of trickery in Excel. So let's get started with that. Just a quick review. We're doing mark recapture analysis in this lab. There's 2 different types of mark recapture analysis: closed population and open population. Closed population is simply for estimating abundance. That's the only thing you can estimate, because closed population assumes complete closure of the population to immigration, emigration, mortality, and births. And so you really can't estimate anything. If you make that assumption, there's not really much to estimate besides abundance. And then open population relaxes that assumption so that we can estimate things like survival rate, recruitment, and even immigration, emigration if we have that kind of data. So those are the different types. And the most basic concept of capture mark recapture is that when we go out and survey a wild population, the detection probability is imperfect. We do not see all the individuals, so one of the key estimates we have to make before we can start estimating things like abundance is to estimate the capture probability. That is, when we go out and do a survey, what proportion of the population do we actually see? And that gives us an estimate implicitly of the portion of the population that we did not see, and that is critical. Of course, we know how many we did see. We need to estimate how many we didn't see if we're going to estimate abundance. And in order to estimate survival properly and that kind of thing too, we have to factor in the probability of detection, because not seeing an individual that may have been marked in the past is not enough evidence to say that the individual is dead, because we may have just missed it. So we have, for both open and closed population, critical parameter here is the capture probability. So that's just a quick overview of capture mark recapture. Closed population models, we're going to talk about 2 different types of models and have a chance to do both in Excel. One is the Peterson model. It's the most basic closed population mark recapture model, and it requires just 2 visits, 2 surveys. You go out once, mark every individual you can capture, release them back into the population, they mix freely, and then you go back again and again capture as many individuals as you can and record for each individual whether it had been marked previously. And that's all the data you need. You have M representing the total number marked in this first survey occasion. You have C, which is the total number of individuals captured in the second survey occasion. And you have M, which is the total number of individuals marked in that second occasion. Critically, you now have M, sorry, I think I said that wrong. You have, yeah, sorry. M is the total marked in the first capture occasion. R is the total recaptured in the second occasion. Did I say that wrong again? And you go out in the first survey occasion, you capture as many individuals as you can, you mark them, that's M. You go out a second time after you've released all those marked individuals, you go out a second time, you capture as many individuals as you can, that is C, and then you count up the number that are recaptured, and that is R. I think I might have said M for recapture. I'm sorry about that. So R is the number recaptured in the second survey occasion, and M is the total number marked in the first survey occasion. So critically, you have the ratio of marked individuals to captured individuals in that second capture occasion. That is the critical part that gives you an estimate of the capture probability. And that essentially gives you the proportion of individuals in the population that are marked, right? So you go out and you capture 8 individuals in that second capture occasion, and 4 of them are marked. Well, that tells you that, at least your best estimate now is that half the population is marked. How many were marked originally? Well, let's say M is equal to 10. Now we can say, okay, well, 10 represents half the total population because we know that half the population is marked. 10 is the number of marked individuals. So all we have to do is multiply by 2 and we get the total abundance. So because we know there's 10 marked, there's probably 10 unmarked because there's half the population is marked. So the total population is 10 plus 10 is equal to 20, right? And let's imagine a different scenario where we go out and capture 10 individuals and mark them and release them in the first. So M is equal to 10. Now we still go out the second time and we capture 8 individuals, but we only see 2 of them marked. So only 2 out of 8 individuals are marked. That's a quarter of the population, right? So that is basically saying that those 10 marked individuals represents a quarter of the population, right? So we have to multiply that by 4, and our estimate of abundance now under the Lincoln-Peterson estimate is 40. So that just illustrates in the really most simple way possible how closed population mark recapture works. We have to be able to figure out what the total proportion of the population marked is. Once we know that, we can easily extrapolate to figure out the total abundance. And by the total percent of the population marked, well, that's the capture probability essentially, because the lower the capture probability, the less percentage of the population you'd be able to mark in that first survey, right? And so the lower the capture probability is, the higher the estimate of abundance is, because the more individuals that you probably missed, right? All right, so does that all make sense? Thumbs up. Okay, so that's the Lincoln-Peterson estimate. We can generalize the Lincoln-Peterson estimate a little bit by using this Schnabel estimate, which is, what if there's more than 2 site estimates? So in the lab, you're asked to do both the Lincoln-Peterson estimate and a Schnabel estimate. A Schnabel estimate can be, 3 or 4 or 5 visits, or any number of surveys can be accommodated by the Schnabel estimator, but you're estimating exactly the same things. You're estimating the total abundance of the population and the variance in the total, sorry, my dogs, and a variance in the total abundance. That is the sampling variance, or the uncertainty around that parameter. So in the lab, you're asked to do both things. For both the Lincoln-Peterson and the Schnabel, you're asked to estimate abundance, and you're asked to estimate the standard error on abundance, or the sampling variation, which gives you a degree, it gives you some idea of what the uncertainty around that estimate is. So just a couple additional notes before we go on to the Excel. The estimate from the Lincoln-Peterson is known to be somewhat biased, which is the Lincoln-Peterson estimate is just C times M over R, C being the number captured in the second occasion, M being the total number marked in the first occasion, and R being the number recaptured in the second occasion. So CM over R is the estimate of abundance in the Lincoln-Peterson. That's known to be slightly biased. So we use this bias corrected Lincoln-Peterson estimate, which just adds 1 to M, multiplies that by 1 plus C, and then divides all that by R plus 1. And then you subtract 1 from that total quantity. And so it's just a slight modification that is known to be less biased in most cases. And the variance of the Lincoln-Peterson estimate, now you're not doing statistics until you also quantify the degree of uncertainty around your estimate. Just having an estimate isn't enough. Like if you're trying to estimate abundance, we are not satisfied if we just have a point estimate of, say, 100 individuals. Well, how certain are we that there's 100 individuals? Maybe we're really certain, and the degree of uncertainty would be somewhere between 90 and 110, and that'd be great. But what if we have much more uncertainty? What if the uncertainty is really from 20 to 250? That is a very different result. And so we have to do more than just quantify the point estimate of what abundance would be in this population. We have to know how certain we are about that estimate. So to do that, we have to compute the sampling variance, and that's been done for us. We have a formula to calculate sampling variance, and it's this, and it's using the same quantities that were used to calculate abundance. Under the Lincoln-Peterson estimate, we have M, C, and R, and we're just combining those in a way that statisticians have worked out is a good estimate of the sampling variance. Once we have the sampling variance, we can compute the standard error as the square root of the sampling variance. If you've taken a stats class, this might make sense. If not, I'm not going to explain that right now, but this is an estimate of the, it's called the standard error. It's an estimate of the uncertainty around an estimate. And from the standard error, you can compute a confidence interval. And the confidence interval is just taking the estimate you have, this n hat would be the abundance estimate from the Lincoln-Peterson, and then plus or minus basically 2 times the standard error. So on either side, you put 2 times the standard error, and that gives you a confidence interval that describes the uncertainty around your estimate. And so that's what you're asked to do for both the Lincoln-Peterson 2-sample estimate and the Schnabel multiple sample estimate. All right. These assumptions are that the population's closed, obviously, for this. The marked individuals from the first sampling occasion mix completely with the population. That is another assumption. Capture probability can differ between visits, but within visit, all individuals have to be equally catchable. And marks cannot be lost between sampling occasions. That's a key assumption to all mark recapture methods, that marks are not lost. And that capture and marking does not affect the detection probability. Sometimes animals get so-called trap shy, or they start to understand that you're there to capture them and they don't want to be captured, and they will stay away from you because they were captured before. Well, that violates an assumption of the closed population mark recapture models, because we have to assume that all individuals are equally catchable at each of those time occasions. If there's trap shyness, we can get a severely biased estimate.
And there can also be trap happy individuals who are very motivated by food. And,
if you put food in your traps, that's even more likely that the animals will become.
Is that the assumption of marks not being lost? Is that basically saying that there's no mortality in the system at that point?
That's the closed population assumption. So that first one is the population is closed geographically and demographically. That assumes no mortality.
Okay.
The marks lost is actually, say you use ear tags on a small mammal and the ear tags fall off. That means that any individual that you capture that had an ear tag before might have lost its ear tag, but you'd be counting it as a new individual when in fact it's a recap. And the number of recaps is super important for estimating abundance.
Right, okay.
So, yeah. Good question. So yeah, the Schnabel estimator is just sort of a weighted average of Lincoln-Peterson estimates, and it's computed just as this formula. So what does that formula actually mean? Well, let's think about it. It looks a lot like the Lincoln-Peterson formula. You have MT time, well, M just being the number of marked individuals in the population, but it's a little different because it's the number of marked individuals in the population prior to any given survey. So at survey 4, M is the sum total of individuals marked in visits 1, 2, and 3, right? So that is what M means, total number of marked individuals in the population just before the current site visit. C is equal to the number of individuals captured. That's an easy one. That's the number of individuals captured at each survey. And what's the other one? R is the number of previously marked individuals captured in the current visit. So that's pretty easy as well. That's the number of recaptures during a particular visit. So C and R are very similar to what they were in the Lincoln-Peterson. And M is 2. It's just a little bit, it's just a, you just have to keep in mind that it's cumulative. It's the total number of marked individuals prior to the current survey. All right, and so once we have those, we can compute the estimate of abundance just as the sum of the product of M and C divided by the sum of all the recaptures. And the sampling variance can be computed relatively simply as the sum of, well, okay, the sampling variance on the inverse of the abundance, which is something I'll talk about in a second, is computed relatively straightforward, just using the same quantities, R, C, and M. And since that gives you uncertainty for the inverse of N, we have to do a little bit more trickery or mathematical manipulations in order to compute the confidence interval. So one way to do it is just to take the inverse of the abundance estimate that you computed up here, and then add 2 standard errors on the inverse of the abundance and subtract 2 standard errors of the inverse of abundance computed right here. As well, the square root of this quantity would be the standard error, and 2 standard errors on either side on the inverse of the abundance. And then once you have the confidence interval on the inverse of abundance, then you invert that and take the inverse of the lower bound, the inverse of the upper bound. And then you'll have a lower and upper bound on abundance rather than on inverse of abundance, which is something that we don't think about very much. Is, you know, we think much better on the scale of abundance than in the 1/over abundance scale. So that's what we're going to do. And that's all you're asked to do as part of this lab, is just to get those estimates. And it sounds simple because these formulas are super simple. But I gave you a fairly long capture history. And this is because that's what we're generally working with. We have capture histories and we have a lot of individuals, and it's a good thing to know how to do, how to manipulate these capture histories in Excel and compute these estimates. So let's do this as a demo. If you haven't already loaded the Excel file, you can get it from this link here, but I will load it up from my, let's see, that left table, it's not that one. Simple closed base Excel, there it is. So I have to enable editing, but hopefully you have something that looks like this in your screen. So let's first do the Lincoln Peterson. So what I'm going to do is just copy this all into a different sheet so that this will be the Schnabel sheet right here. I'll just rename that Schnabel, and this is Lincoln Peterson. All right, LP. Okay, so let's go back to the Lincoln Peterson. I'm just going to delete the rest of the samples because Lincoln Peterson is just a 2-sample estimate, right? So I will delete those. And now we have capture histories. So each of these rows represents an individual. Each of the columns represents a site visit, right? So we have sample 1, sample 2. So what do we need in Lincoln Peterson? Well, we need the total marked, right? The total marked population. We need the total number captured in the second survey occasion, and we need the number of recaptures, right? So if we have those, then we can compute the Lincoln Peterson abundance estimate. So these two are easy. What's the total number marked? Well, all we have to do is add up all of the first sample. Ones represent individuals that are seen, and we assume they were marked and released back into the population. And so we just have to get the sum, and we should have 137 marked. Now, to get the total number captured in the second occasion is the same thing. We just have to add up all the captures in the second occasion. So that is equal to sum, that's not an equal sign, sum of sample 2. Sum all that up. And now we just have to compute the number recaptured, right? One way to do that, there's lots of ways to do this, but I'm just going to make another column. Is it a recap? So if it's a recap, we should have sample 1 is equal to 1 and sample 2 is equal to 1, right? So they both have to be equal to 1. So it really has to be that both sample 1 and sample 2 are equal to 1, right? So that would be one way to think about it. So say if equals, if else, if oh, I'm no wizard with Excel. If some of those equals 2, then it's 1, otherwise 0. And let me just copy that all the way down. And now we should have something that tests if there are recaps. There are easier ways to do it. I'm just doing the first thing that comes to my head, but hopefully that makes sense. And now recaps is equal to the sum of this whole column. And so we have 42 recaps, right? And so now we can estimate abundance. So N is our estimate of abundance, and that's equal to the quantity C times M divided by R, right? So far, so good?
Yeah,
okay.
I was hoping you could describe what the zeros represent in that first sample, since it's
so
not very intuitive for somebody to not be.
Yeah, every individual that has ever been captured either in sample 1 or sample 2 in this case are given a row in this capture history, right? So every individual is captured either in the first or the second, is given a separate row. Capture history represents, individuals on the rows and, visits on the columns, and every column represents a different visit, and it's a 0 if it wasn't seen, if an individual was not seen at that visit, and it's a 1 if the individual was seen at that visit, all right? And
so in this case, we have zeros in both columns only because we decreased our sample size. We're only using our.
If you look at the Schnabel at the full data set, those individuals were captured later. Yeah, so you wouldn't normally, if you just had 2 total surveys, you wouldn't normally have 2 zeros, but it doesn't actually affect the analysis at all. But that's a good point. Thank you. All right, so we have an estimate of abundance. What we might want to do is to get that less biased estimate of abundance. So let's get, we'll call that N2 or N unbiased. And that was going to be, so let's let's put 2, so that's C plus 1 times M plus 1 and divided by R plus 1, and then take that whole thing and then subtract 1. So we're just implementing that unbiased formula, and there's a problem with the formula because I did it wrong. What did I do?
You just used the letters C, M, R.
God, my brain right now.
It's okay, I didn't notice it until right at the end there when you were about to hit apply.
Thank you. Yeah, so the correct unbiased estimate is 374.48, or basically 374.5. That's the unbiased estimate of abundance under the Lincoln-Peterson. And now we have to apply the formula for variance of the Lincoln-Peterson estimate. So we want to get this here. Would one of you be able to like read that out to me as I put it in Excel?
Yes.
Because I'm not going to remember it in my head right now. All right. So this is variance on abundance. All right.
I'm just trying to get over to my screen where it has the correct equation.
So
okay.
This, yes.
And then put this guy bigger.
So the numerator.
Numerator is m plus 1.
And
137 there.
M plus 1, yeah.
Times C plus 1.
Times C plus 1.
Times M minus R.
Times M minus R, yeah.
Mm-hmm. Times C minus R.
Times C minus R, yeah.
That's the numerator.
Okay, divided by denominator.
Yep. The first part is R plus 1 squared.
Okay, R plus 1, keep doing that, plus 1 squared.
Multiplied by R plus 2.
Okay, and that's R plus 2, all right?
And that should do it.
So the variance is 1,395, and now we get the standard error as the square root of that, equals square root of the variance. So the standard error is 37.35, and then the confidence interval, lower bound, is equal to your unbiased n minus, I'll just say 2 times the standard error. That's kind of a good lower bound of 299.7, and the confidence interval upper bound for abundance is equal to the unbiased n estimate plus 2 times the standard error, and that should be 449. So we have a estimate of 374, a lower bound of 299, and an upper bound of 449. So we don't have great precision on that, but it's really important for us to know that because the population really could be almost 500 basically, or it could be as low as about 300. So we have a lot of uncertainty there, and that's typical for a 2-survey abundance estimate. Any questions before we move on to the Schnabel?
Do you have a quick, easy answer on why you multiply the standard error by 2 before?
It comes from the T distribution from statistics, where a standard error kind of represents a normal distribution of uncertainty around the estimate of the mean. So if you think of a normal distribution, most of the density of a normal distribution with a standard deviation of 1 falls within 2 standard deviations of the means, all right? Basically, or within 2 of the means. So most of a normal distribution falls within 2 standard deviations of a mean. Most of your uncertainty about an estimate falls within 2 standard errors of your estimate. So it's the same logic there.
So you were basically just rounding up that 1.95 to 2.
1.95 is what? Yeah. Sorry, that's the T distribution. Yeah, I think it's like, is it 1.95? To get the exact 95% confidence interval, you would take a critical value from the T distribution, which, with a certain number of degrees of freedom as represented by your data, and then that might be 1.95. In this case, you multiply that by the standard error and add and subtract that. So plus or minus 1.95 standard errors. Yep. So that's an approximate confidence interval though, right? All right, so let's move on to the Schnabel estimator. It's the same sort of thing here, but now we have multiple visits. And so we still have the same kind of thing where we want to know, you know, C, the total number captured in every given survey. We want to know R, the number of recaps that we identify in every given survey. And we need to know the total number of marked individuals. But this time, the total number of marked individuals keeps increasing with every survey, right? So it can be useful to try to like identify individuals that are newly marked basically in each survey. And that can be a good intermediate step. So let's just do that. If I had done this prior to this meeting, this would go smoother, but I will, hopefully, we'll get through this, right? So what I want to do here, and I'll just talk you through what I want to do, and hopefully that'll lead us to what we will do, is to identify the number of newly marked individuals here. So of course, there's not going to be, the only newly marked individuals here are going to be the ones that were captured because there's no previous surveys. So for sample 1, we can just copy that directly in here. So we'll just copy that first visit because those are all newly marked anyway. We know they're newly marked because nobody's been surveying this population prior to that. Now we have to start developing a way to get at which of these are newly marked. So if it's newly marked, we should see a 1 here and a 0 here, right? So if we subtract sample 2 from sample 1 for every individual, all the 1s basically represent newly marked individuals, right? So all we have to do is just say that's equal to sample 2 minus sample 1. And all the 1s are going to be newly marked. If it was marked before, it will, well, okay, there's one more thing we have to do. Because this could be -1. If it was not seen in this and seen before, that's going to be -1. We only want the 1s, right? So to do that, we can just take the maximum of 0 or the difference between sample 2 and sample 1. That way, if it's -1, 0 is greater than -1, right? Or wait. So we take the max of that, right? 0 or -1, the max of those two is going to be 0. So 0 is what we want. It's basically 0 representing we did not, this is not a newly captured individual, right? So that way, only the ones that have a 1 in sample 2 and a 0 in sample 1 will be 1. Everything else will be 0. And that's what we want. So I will just double click on this here, and that will give us 1s for everybody that's newly marked in sample 2 and 0s for everybody else. Okay. So far, so good?
Yeah, it's just not going to account for recaptures, right?
Well, we'll get there because recaptures are the difference between the total number of individuals captured and those that are newly captured.
Right, okay.
So if we can get the number newly captured, we can calculate the number of recaps.
Okay.
This is, we'll see. We may run into issues because I didn't go through this first. So sample 3, let's go through it. So we need to figure out all the newly captured individuals in sample 3. We can use the same basic logic, except now it has to be a 1 if it was captured in sample 3 and not in sample 2 and sample 1. That means it's newly captured. All the others should be 0, right? So we can kind of use the same logic where we say we'll take the maximum of 0 and basically the sum of all the previous captures, right? So here it's let's take equals to sample 3, and if that minus the sum of the previous 2 captures is 1, then that means that this is a newly captured individual. If the sum of these two, sample 1 and sample 2, is 1 or 2, right? Or 0. Well, no, if it's 1 or 2, if sample 3 is 1 and these are both 0, that's what we want. We want it to be 1. If this is 1 and the sum of these is equal to 1 or 2, that means it's a recap. So we don't, it should be 0 under this scheme because it's not a newly captured individual. So now we can just say the max of 0 or C minus the sum of the previous 2, that's going to do what we want. So that's going to be, it's going to be a 1. If it was captured only in 3 and not in 2 and 1, and it's going to be 0 otherwise. If the sum of these, if this is a 1 and the sum of these is 2, that's -1. The max of 0 and that is 0, so it's going to be a 0. So anything newly captured in sample 3 is now a 1. Everything else is a 0. These are newly captured, right? So it looks right. It's doing the right thing. These are newly captured in 3, right? All right, and so now we basically have a scheme that will work for all the rest. So we don't have to like keep going through. We can actually say, let's do this is the sum of, we'll fix A, we'll fix column A, and now we'll let the others sort of drag with us. So let's put a $sign before the A there, and let's refill it down. It won't change the answer here, but it does mean that we can then highlight all of this column and just drag over a few for survey 3, survey 4, survey 5, and survey 6, right? And now we should get all the newly captured individuals in every survey. And let's just make sure that that works. So here, this should be first captured in 4, and it is. This should be first captured in 2. And let's go up to the top. Let's make sure those worked. These should be only newly captured in the very last survey, and it is. So this represents now the new captures, all right? All right, so let's do a couple additional things here. Let's sum up the total.
Never applied an equation dragging to the right before. I'm always used to seeing it go down, so I was like, what is this sorcery?
Excel magic.
Nice. So, now I've learned a nice new trick today.
Cool. So let's calculate the sums of each of those. In fact, let me just move it down so that it's easier to see. This is going to be sums. And so I'm now going to just sum up these columns and just drag all the way down to get the sum of the number of captures, right? All right, so that's the number of captures in the first column. And I should be able to just drag that over to get the number captured in all the other columns. So that's C. We already have C now, because that's the total number captured in every survey. Now let's sum up this. That's the total number of new captures, right? So the total number of new captures is should be equal, it should be the same for the first visit. So I think we can just copy this and drag it over. So I just copied and pasted, and that should be the right numbers. Now this is column H in my version. So now I can just drag this over to get the total numbers of newly captured individuals in every survey, right? So that doesn't give us anything directly, but it does allow us to start to get at the number of recaps. What is the number of recaps? The number of recaps is just the total number captured minus the number that are newly captured, right? Because that means that they were captured, but they weren't new, which means they had to have been a recap. So to get the number of recaps, we just take the total number of captures minus the total number of new captures. And of course, in the first visit, that's zero recaptures. But if we drag that over, we should get the total number of recaptures, and it's going to increase because by the end of the survey, we've captured clearly a big portion of the population here because look, we've had 9 new captures and 150 recaptures in that last survey occasion. So out of 159, 150 of them were recaps. So that means, as the recap is going up, that's telling us we've captured now and marked a good percentage of the population, which is good. Should mean we'll have a more precise estimate of abundance. So we have R, we have C, and I could even change this to C. So we have C and we have R, right? And in fact, maybe we want to put those somewhere where we're more likely, where it just will look a little better here. So here we have, let's summarize what we have. So for sample 2, sample 1, sample 2, all the way through sample 6, we should have C, R, and M, right? Those are the things we need. We already have C, which is equal to this here. And then I'll just move that over. So now we can get the C's, and we have the R's, right? And the R's are just the number of recaps that we just computed. I'll just move it down from the bottom. Oh man. And just drag it over so we have the total number of recaps. So we have total number of recaps. Now the only thing we have left to do is to compute the cumulative marked individuals in previous samples. Now, obviously that's going to be 0 in the first occasion. There's nobody previously marked, right? But once we start to get here, we do know that there are some marked. How many marked? Well, it's equal to the number captured previously, right? They were all marked. So now there were 137 previously marked individuals in the population, right? Now for sample 3, how many had been marked before?
137.
Equals 137 had been marked, but 137 plus all the new captures, right?
Right.
What are the number of new captures?
116, right?
That's
minus
74, right?
Sorry, yeah. Okay.
So there's 74 new captures. So that is 74 new captures in the second sample, plus the 137 that were marked in the first sample, right? So there were 211 marked in the population prior to sample 3 happening. Well, here, in fact, I think we can drag over from this point because we have R7 representing the total number marked from the previous, so the total number that had been marked prior to the second sample. Now we have to add the total number of new captures in the third sample. So one sec. So for this, I think we can just drag these over, and I think we will get the right numbers now because we just are adding up what was what had been marked in the population previously to any new captures that had happened in the previous occasion, right? So this should be all we need. We have total number captured, total number recaptured, and the total cumulative total number marked.
I don't know.
No, I think I did it wrong. I think
Shouldn't it be when you're adding, it should be the difference between C and R that you're adding to the new?
Well, that would be probably an easier way to do it. Let me just figure out what I'm doing wrong. I think what I'm doing is I'm adding up. Yeah, because so it did work for this one, right? You take the total number that had been marked and then you add the number of new captures, right? But I think I'm doing something, I'm cumulatively building up in a way that I probably shouldn't be. But I just want to make sure. So, okay. Let's take this. We have 211 that had been marked, and then we add J343. J343 is equal to the total newly marked there, right? And that's good. And here you take the total number that had been marked prior to sample 4, and you add the number that were newly marked in sample 4, right? 1, 2, 3, 4. I think it's right. Let me.
Makes a lot more sense than what I came
up with. It was some, I don't know what.
Yeah, what just happened with that
evil spirit, like communicated through the Zoom. So I think that's right. So we have a total of 340 marked individuals by the end. Prior to the final sample, we had 330. Oh no, 339, because that top one is not an actual. So we captured 9 new ones in that final one. So there should have been 330 marked prior to that final sample, because we captured 9 new ones, and out of the total 6 surveys, we marked a total of 339. So that works. All right, so now let's implement the Schnabel estimator. And the Schnabel estimator looks like this. Sum of M times C divided by the sum of R. So all we have to do to get N is the sum of M times C. Here, let's just make this even easier. MC equals M times C, and it's just, so that's the M times C. Now we just have to take equals sum of, sorry, M times C divided by sum of R. 349. 0.74. How does that relate to the Lincoln Peterson? Well, it's within the bounds of uncertainty, right? But it's higher. No, it's, so the N estimate here was 374. Now we have 349, and let's see if we're more sure about that estimate. So we have to compute the standard error. Let's first compute inverse of N, just because we're going to have to be doing this on the inverse scale. So inverse of N is equal to 1 over N, right? So now the standard, so the variance on the inverse of N, it's a little confusing, but let's look at the formula. It's the sum of R divided by the sum of MC squared. I like that, MC squared. We are really doing some serious stuff here. So, all right. So sum of MC squared. Okay. So let's see if I can remember that. So sum equals sum of
R.
Oh, sorry. I already had it wrong.
You're just so excited about the MC.
MC squared. We have the mass energy transition equation right in here. This is pretty amazing. So the sum of R divided by the sum, and I'll put that in parentheses. I hate that you can't use the arrows. I always want to do that. The sum of MC squared. All right.
Or is the square outside of the sum?
Let's look at the formula again. It looks like it's just in the denominator, so it should be outside or inside.
Okay,
right?
I lost it.
So it's correctly inside the. It's part of the denominator. So, so now we can calculate the standard error of the inverse of n by taking the square root of that equals square root of that. So it's 0.000119. Here's the inverse of n. So inverse of n, lower bound, is equal to inverse of n minus 2 times the standard error, and the inverse of n upper bound is equal to the inverse of n plus 2 times the standard error on the inverse of n. And then we can get n lower bound is equal to 1 over the inverse of n lower bound, 381, and the n upper bound estimate is equal to 1 over the upper bound. Oh, sorry. Since it's inverse, it's reversed. I'm sorry. That's the lower bound now on the inverse scale, and this is the upper bound because when we did the inverse, it reversed. So the lower bound of the inverse is the upper bound on the abundance. So, but that is, so we have the estimate of 349 or just about 350, ranging from 322 to 381. Now, we know that it's actually bigger than 330, but since this is just an estimator, because we actually marked 330, and this is a closed population, so there couldn't have been any mortality. So therefore, the lower bound really has to be 330. But since this estimator doesn't take that into account, it actually does go a little bit below the total number captured. But it looks like we did this right. And that's not atypical. So you might instead make the lower bound 330 or just equal to, oh, actually 339, right? Because we captured 9 new individuals there. So I'll just write that in. So really we could replace the lower bound, sorry, that's the lower bound, with 339. So the true uncertainty, because we don't have any uncertainty really about that because we did capture 339 individuals, but we do have an uncertainty about the upper bound. And so the true uncertainty is 339 to 381. And that's a pretty good range of uncertainty. In fact, that's quite a bit better than we did with just 2 samples because our upper bound was almost 450. So we have a pretty good understanding now of the abundance in this population. And so, yeah, we're there. And we did it.
Hey.
Any questions? Cool. And you know, the other part of the lab is pretty straightforward. It's a basic, you know, applying this open population model to try to get an estimate of survival rate. But I do encourage you to just work through it. You can use this library called Mark. It's really easy. Marked. It's really easy to use. We do the same kind of demo within the parameter estimation class, but we can load up this classic European Dipper data. We use these helper functions from the marked package to get the data in the right format. This process data and make design data. We can just get the data in the right format. And we can fit models using this CRM function, or capture recapture model function. We feed it in the data. We feed it in the covariates or any kind of additional supplemental data that we have that we put in to this make design data helper function. But this basically gives it all the information it needs to fit the model. You tell it what model you want it to fit. In this case, you want it to fit a model where survival or phi is time invariant. That is, oh, sorry, this one actually is time dependent. And you also model P as a function of time. That is, you're gonna have a separate estimate of capture probability for every time period in your data set. So maybe you have, you know, five different surveys. I forget how many the Dipper data has. Might be 7 or something. And then you have a separate estimate of survival for every time period as well. And so we can fit that model. It just takes a second to run and print it out, and you get a separate estimate for each time period. So you have 6 time periods that you can estimate survival for. And so we have 6 estimates of survival and 6 estimates of capture probability. And that's, you know, what we told it to do. You can do the same thing with setting up different models. So this time we can set up models that don't vary by time. So this is survival that doesn't vary by time, and capture probability that doesn't vary by time. And we can compare it with models that do have varying capture probability and survival by time. So the phi dot is just the basic, that's how we say basically in mark recapture speak, like a model that is not time variant. So phi dot is an invariant survival rate, and P dot is invariant capture probability. And so we can then create a list of all the models of P and phi that we've specified. We have 4 different models. We can run them all using the CRM wrapper function. It just runs them all, and we can compare them using this AIC table. So in AIC model selection, we just take the model that has the lowest AIC and treat that as the model with the most support. So AIC is just a criterion that we use to help decide which model is better than another model. We have 4 different models that we're comparing, and this model selection table indicates that the model with constant capture probability across time and constant survival rate across time is the best model. That is, I think, all I'm going to say about that. It's pretty straightforward to go through that. I just especially wanted to go through the closed population estimates, because that's kind of difficult, and but it's a useful thing to know how to do. I'm going to stop the recording unless you have questions. All right.
I think the last thing that I would just note, I'm sure this maybe is in the lab or something, but this is all stuff that is going to be covered in a lot more detail in population dynamics, your
Thank you.
EDOT and phi time. And so this is a nice place to see it for the first time before you kind of play around with them more.
Exactly. Yeah. So it's a good chance for you to get a little sneak peek at what you're going to be doing more in, what is it, 488, right? All right. I'm going to end this recording